Hello, good afternoon. My name is Divya, and I'm here to give an overview of our work on digital process monitoring and inspection for terminations and connections in electrical machine manufacture. This work has contributions from Dr. Michael Farnsworth, Professor Tiwari, and our PhD student Alex. So you may be thinking, why terminations? Just to give a bit of background, that before we started the work, we did literature and industry survey. This was to gain an insight or to understand the level of automation and manual activities within EM manufacture in the UK companies. The findings were very interesting, that literature focused heavily on automation, whereas industry highlighted the need for analysis and inspection of manual processes. So the table on the right is showing responses we obtained from 7 UK-based electrical machine manufacturers. And if I can highlight the contacting or the terminations area, where majority of our respondents, they agreed that this particular activity was highly manual, and it was very difficult to automate. So making reliable connections, terminations or joints was difficult to automate, and the percentage of failures attributed to manual activities involved in this activity could be between 30 to 50%. So that discussion with industry and literature review led us to focus on contacting activities. Full details about this study is available at our published article. We have the DOI here. So the first activity that I'm going to discuss is digital inspection for lids wire terminations. As you know, you may know that for lids wire terminations, the process of making terminations comprises of two activities. First one is enamel removal, and second one is actually making the connection. So joining of insulated copper wires with belonging cable lugs is seen in literature as a major reason for motor failures. A review of literature and discussions also revealed that up to 10% of lids wires, which are special types of cables designed to reduce losses, have failed connections due to incomplete stripping of some strands inside the connector. So we obtained this use case from an industrial partner who were very kind to give us the use case. And that led to us investigating infrared thermography as a non-contact, non-destructive process for inspection of enamel removal. Right, so as I mentioned earlier, incomplete stripping of some strands inside the connector makes soldering impossible on those strands. So I took some strands of lids wires. The figure on the left is showing 3 strands, 1, 2, and 3, where the strand 1 had enamel removed, whereas 2 and 3 still had some enamel on them. If you look at the top pictures, they are the infrared images captured when the wire was being heated, and the bottom images represent the cooling cycle. As it is visible from this image, that it's actually during the cooling cycle that the difference between heating, difference between the wires where there is enamel and the enamel has been removed is quite distinct. The fourth thermal image is showing wires 2 and 3 that had enamel quite clearly. This difference we were seeing was due to the difference in emissivity of copper and the enamel film, which was polyamide in this case. We also plotted the temperature decrease rate of copper and the enamel, and what we found that the temperature decrease rate of copper was much greater than the enamel section. Now, after we did this initial study, what can we do next? So we thought, okay, can we make an automated feature detection system that can automatically look at the wire and without a person manually picking out, okay, these are the wires that need further treatment? Can we develop an automated system? So the flow chart shows the process for automated feature detection and quantification of the degree of enamel removal. We first started capturing data that was exported to CSV and ABI. Then masks were constructed. Following construction of masks, we trained some models. And finally, these models gave us very good results that I'm going to talk about in the next slide. First of all, modeling. Different materials have different thermal conductivities, and the cooling period data from the recordings could be used to infer the material occupying the pixel. It was found that the minimum, maximum, and average temperature of the cooling over the cooling period varied more distinctly between classes compared to other matrices. A model was trained on each dataset separately. To train models and to evaluate the result afterwards, a series of masks were constructed for each material present in the recordings and the background. Classification models. We trained around 3 or 4 classification models and compared the accuracy. So basically what these models were checking was, can the strands where enamel still exists, can it be identified accurately so that they can be taken away for further treatment. Out of the models we trained, the SVM support vector machines achieved an accuracy of around 90% in detecting the enameled bias consistently across all the files. We checked the model evaluation time was 3.7 seconds. The second best performance was obtained from Gaussian mixture models, with an accuracy of around 70% in detecting the enameled region. The average model evaluation time was 1 second. Now we have the hardware system developed. We have the thermal setup that can actually detect the wires and highlight which wires need further treatment. We have the algorithm in place. So the next step is we are building a demonstrator for testing the process of enamel removal. And this demonstrator, we hope that if we can take it to the shop floor of any company, whoever can help us with that. And when the process is being carried out, when the enamel removal process is being carried out, can we use this demonstrator for process inspection there and then, in process inspection? So this was an update on process inspection for enamel removal. Now I'm going to talk about other activity, which is process monitoring for leads wire soldering. So we talked about inspecting, and now we are monitoring the activity of soldering. The solderable leads wire we obtained we obtained it from German company called Electrisola. And we took it to a local SME that specializes in build and repair of electrical machines. And what was found that, so what happened was we took our sensing equipments, we took thermocouples, vision systems, etc. when the termination was being built. And what was found that the solder pot, the temperature it was reading and the thermocouple we put in, there was a huge difference in the two readings, up to 10 degrees in some case. And it was found that just by a couple of degrees or up to 5 degrees temperature in solder and half a second difference in dipping time can lead to a massive difference in the impact on solder quality. Later on, we looked at other process parameters and sensing techniques. So the first one, soldering, I have already discussed. Then we did the visual inspection of the joint using RGB techniques. Can we calculate the area and volume of solder on a particular joint? So the rows highlighted in green are the activities that are more or less complete. And now I'm looking at the other rows in yellow. I'm going to focus today on the X-ray CT and infrared imaging of the joint. So why X-ray CT? So when a joint is being made, it is capped inside the lug. Can we check, compare it with process parameters, the porosity, the solder fill to determine the joint quality? And then I'm going to talk about we are using infrared imaging techniques when high current is passed to check the quality of the joint. So CT scan of termination samples. we kindly received some termination samples from industry. And to understand the relationship between process parameters such as solder quality, temperature of the solder, contamination, etc., on the quality of the joint, we performed a CT scan image of the termination. After CT scan, I conducted image analysis to calculate the percentage of porosity, percentage of solder fill in the soldered area. This was very important, as you can imagine that porosity is bad for connectivity and heat dissipation. This CT scan study also allowed, if I can, so there's a video. Okay, so I had actually prepared a video that showed the three-dimensional view of the joint from end to end, but for some reason it's not playing. How do I play it? No problem. I'll move to the next slide. Right. The other study that I'm going to talk about is quality assessment for terminations using a combination of RGB and infrared imaging. So following the study that I've already discussed, that led to starting of a new PhD in this area. So my student Alex is looking at quality assessment for terminations using a combination of RGB and infrared imaging. So if you can imagine, in a joint or in a termination, there are some features that are visible that you can see. For example, if the bent area is crimped, if the insulation is burnt, if more insulation or less insulation area is burnt than usual. These are the features that are visible and can be captured using just simple RGB imaging. But then there are also features that are hidden underneath. For example, porosity, air gap, that cannot be captured with RGB imaging. So first, looking at the visible features, which are the surface defects. We used VGG16 algorithm and trained it to look at the surface features. For example, in this case, if there was a spike or no spike, if the sample was good or bad. And we achieved 100% accuracy with VGG16 for defect or no defect on the defects that are visible, that can be actually seen using our RGB camera. The other classes that we are going to add is if the crimp is bent, what about the area of insulation, burnt insulation, is it more or less than what it should have been? Okay, so I talked about visible defects. Now, what about the defects that are underneath the surface, that are not visible? Can we catch them? So, in order to catch the invisible defects, we have started using infrared imaging and analysis to catch the unseen defects. So a very high current was passed through a termination sample that we obtained from industry. And this high current was passed through a test rig that Steve kindly allowed us to use. He has developed for his work. When high current was passed through this termination sample, we divided the whole region into small regions of interest. And heating and cooling rate of those regions of interest was studied. And it was found that some areas were much hotter than other areas. Some areas were cooling at a much faster or slower rate compared to other regions. Okay, so that's fine. We don't know what's underneath. How do we understand what is happening there? Then we had the CT scan images. So the next step was to compare these infrared images with the CT scan images that we obtained earlier. Can we locate the air gaps by analyzing the rate of heating, cooling, or the temperatures that we have seen? It looks like we can, although these are very initial studies, but we can. So what we have so far found is that the regions where there was significant air gap, those were the regions that were the hottest, in the whole of the sample, and they were actually cooling at a much faster rate compared to the rest of the region. Although these are very initial results, and Alex needs to do more experiments to compare more samples, more experiments, but this is what we have got so far. And it looks like we may be able, by comparing the thermal imaging, infrared images and CT scan, it may be possible that we can look at the hidden defects using thermal imaging. Finally, I'm going to talk about a case study that was conducted by Dr. Michael Farnsworth. This work was developed as part of a short proposal that was written by Dr. Michael Farnsworth with TWI. Here, the main aim was to capture the process parameters, which is the tip of the welding and the speed and the defects. And if those process parameters or the result could be fed back to the operator to change or make settings in real time. 3 error classes were the focus of this work, which are excessive sidewall fusion, lack of sidewall fusion, and splatter. And in this work, there was a comparison made with traditional machine vision tools versus deep neural networks in detecting the tip and if a defect could be identified. So the bottom figure shows the 3 techniques that were used to detect the tip of the arc. So first one is MIL tip tracker. Second one uses canny edge detection to detect the tip. And third one uses circle algorithm. With the use of deep neural networks, 90 to 95% of classification accuracy was obtained in identifying the type and classifying the right error. There are the 2 videos that show example of tool and DNN object detection and instant segmentation for TIG welding, splatter and tip. On the left-hand side, the tip is being tracked, and if you can see, the errors are being detected in real time, which is excessive sidewall fusion error, splatter error. All the 3 errors are being detected. The right-hand side figure shows the TIG welding segmentation using deep neural network, where we have stated that 90 to 95% accuracy was obtained in detecting and classifying the right error. And finally, I'm just briefly going to touch on some of the future work that we are planning to do. As I've already discussed about the various techniques to make terminations, finally, just a bit of update on the thermocrimping or the hot crimping technique. Thermocrimping technique combines high process stability with short takt time. So it is a technique that is of huge interest by industry and academia. However, in this particular process, defects such as improper insulation melting, melted burnt wires, etc. result in highly frequent setup processes. And it's important to understand the process parameters that affect the final product. In order to understand this, our next step is to have a lab-based thermocrimping machine that could be instrumented with a variety of sensors, for example, vibration sensors, vision sensors. And data acquired from these sensors would be assessed, and sensor fusion techniques will be used to identify the most meaningful sensors and data. And this study will again aid in understanding the impact of process parameters on final product quality. That's all from me. Thank you.